Hello, my name is Emanuel Vintila, and this is the presentation of Mesh, a memory-efficient safe heap for C and C++. This project has been done at the Fraunhofer Institute in Germany. First, I will briefly present the problem statement, which is the presence of memory vulnerabilities in C and C++. Then, I will go over the existing solutions to this problem. Finally, I will present Mesh, our heap protection mechanism, and evaluate it from a performance and security perspective. Memory vulnerabilities in the two languages are of two types. Spatial memory vulnerabilities are about going outside the bounds of objects. If we imagine X, a 4-byte array of characters, shown here in memory with green, then a spatial memory vulnerability is going outside the bounds of this object, in this example writing to the fifth element of the array. Temporal memory vulnerabilities are about using objects after they were deallocated. For example, if X is freed, then its memory becomes deallocated to be reused by other objects. However, the X pointer is still usable for reading or writing to the memory region which was previously allocated for X, but cannot be used by another object. To tackle these problems, memory safety is needed. For this, we make use of additional information about objects called metadata. Namely, for spatial safety, we need to know the bounds of the allocated object, such that each memory access is checked to be within these bounds. For temporal safety, we need to know if the object is still allocated. In other words, if it is still alive. When X is freed, its entire memory becomes invalidated. We can know about this by looking at the alive state flag. Now, to existing solutions. One way of achieving memory safety is to use fat pointers. A fat pointer is a structure that encapsulates the old pointer alongside its metadata. In practice, this metadata is usually just for spatial safety. If one wants to achieve temporal safety using this technique, expensive computation is needed. For example, imagine that multiple pointers point to the same object. If one of them is used for deallocating the object, all the other fat pointers need to somehow be notified that the underlying object is no longer allocated. One example of a solution that uses this technique is secured. Another family of solutions uses shadow memory. For example, the address sanitizer is one of the most widely deployed memory solutions out there. Each byte in the memory of the program is shadowed in a different memory region for storing metadata. Each access to the normal memory is checked against the metadata in its corresponding shadow memory. However, this technique usually doubles the memory of the program, or even more. Other solutions, for example the hardware address sanitizer, make use of the fact that in practice not all the bits in a pointer are used for storing an address. For example, the two mainstream 64-bit architectures only use 45 or 46 bits for storing the address. Pointer tagging techniques make use of these free bits to store a link between the pointer and its corresponding metadata. Our solution is one of the techniques that uses this solution, as I will describe in the following minutes. One of the biggest problems with existing solutions is that the ones that ensure both temporal and spatial safety use up lots of memory and are also usually slow. To address this, we propose a solution which is both precise and memory efficient, called Mesh, or a memory efficient safe heap. To present this solution, I will start by stating what we are aiming to achieve. First, we want to detect both kinds of memory bugs in the heap memory region. This includes accesses from outside our protected heap or from unprotected pointers. Then, we focus on usability. We want to support C and C++ as they are, without requiring any modifications. In other words, we want to be able to compile already existing code without changing it in any way. Moreover, in practice, most programs make use of external libraries, which is usually precompiled code. This has to be supported by Mesh for it to be usable in practice. Finally, we aim to impose virtually no memory overhead, as this is one of the biggest problems of existing solutions. While slowing down the program can be accepted, sometimes there simply is no more memory to use. As mentioned before, to achieve memory safety, we need metadata. In Mesh, we store both the temporal and the spatial metadata in a table, which we call the Mesh table. To map pointers to metadata, we use the pointer tagging technique to directly store the table index inside the unused bits of the pointer. Now, to better understand how mesh works and how it achieves the previously described goals, we will look at operations that can be done on objects and pointers in C and C++. To start, we look at allocations. We need to intercept C standard library allocation function calls and C++ allocation operators and store the corresponding metadata for the allocated object in a line of the table. We then store the table index inside the unused bits of the pointer. In this example, if we imagine that the corresponding metadata line for the pointer x is the line number 1, then we simply store 1 in the unused bits of the pointer x and use this to map accesses through x to the metadata line 1. When deallocating an object, we use the table index contained in the tag bits to set the validity flag corresponding to this object to false. Later accesses to this object will be detected even when done through derived pointers, as opposed to the fat pointers technique. In mesh, pointer derivation remains as it is. When copying a pointer, the copy is done by value, so the tag is propagated alongside the address. Moreover, the tag is not affected by pointer arithmetics. In this example, if we derive y from x, the value of y is just the value of x plus 2, which does not affect the most significant bits of the value, which contain the tag. Casting also remains unchanged, as it is just a reinterpretation of a value for a different type. The last operation that I want to talk about is dereferencing, which can either be for reading from or from writing to memory. Dereferencing is where the spatial safety checks are performed. For this, we use the tag to extract the spatial metadata from the mesh table and check to make sure that all the accesses are within the bounds of the allocated object. For example, imagine an illegal access through our pointer x. Because the access address is greater than the upper bound of the object, an overflow is signaled. Then, the temporal safety check is done on both dereferencing to detect use after free vulnerabilities and on the allocations to detect double freeing. For example, imagine that x was freed. Later accesses are detected because the validity flag in line 1 is set to false. Note that derived pointers, such as y in this example, contain the same tag, and accesses through them are detected in the same way. Finally, we want to prevent other pointers from accessing our protected heap. This can be done by making sure that all accesses through untagged pointers are done only on other memory regions. Now, to conclude the security call, I will present some of the most important optimizations that we have made for our prototype implementation. First, we know that the validity flag does not have to be explicitly allocated. We can initialize the entire table with maximum values and use this value to signal invalid lines in the lower bound. Then, when a deallocation is performed, we just set the lower bound to maximum. This allows us to merge the check for a temporal safety with the one for underflows by checking that the accessed address is never smaller than the lower bound, which is either the lower bound of the allocated object or maximum in case the object was deallocated. Then, we take a look at the checks done on untagged pointers, which can be very costly. If we move the mesh heap low in memory on the first usable page, we can merge the two checks for determining if an address is within our heap to just one. Now, to proceed, let's look at compatibility, which is the second family of goals that we have identified. For this, we know that we only need to have unused bits in pointers, which is by default the case in both major 64-bit architectures. We also know that we don't need to fatten pointers using structures, which allows us to preserve the default function call conventions. Moreover, as mentioned before, casts are supported without modifications, as they are just reinterpretations of values for different types. To support external libraries, we need to allow pointers to the normal heap to be used alongside pointers to the mesh heap. For this, we make use of the fact that such pointers have their unused bits set to 0 by default. We then use 0 as a tag for denoting unprotected pointers. Such pointers are, however, not allowed to access our protected heap. Moreover, when calling external functions, pointers must be stripped of their tags for them to be usable in the external code. Our last goal is about the memory impact of our solution. First, we know that our pointers maintain their original size, so do not increase the memory impact at all. The memory impact is fully determined by the size of the mesh table, which is 2 to the power of t times the size of one line, where t is the number of unused bits in a pointer. For example, on x86, 17 bits are unused, so the table can be at most 2 megabytes. This, however, leads us to the main limitation of our concept, which is given by this number t. Since we only have t unused bits, we have only 2 to the power of t lines in the mesh table. This means that we can only have 2 to the power of t objects. One possible solution to address this limitation is an optional wraparound and reuse algorithm. Imagine that the program has allocated all the 2 to the power of t lines. We can then wrap around to the start of the table and start reusing lines that have since been invalidated. This, however, can introduce a probabilistic temporal vulnerability. Imagine that we have a dangling pointer to a very old object that has since been deallocated. Accesses through this pointer are cases of use after free. However, if the wraparound and reuse algorithm reallocated that same line, then the dangling pointer can be used without detection, if of course the access address is within the lower and the upper bounds of the new object. Another, better solution is to simply use more bits. For this, we can use the most significant bit to denote if a pointer is tagged or not. If the value of the bit is 0, then the pointer is untagged and the address bits are used as they were. Otherwise, if the value of the bit is 1, then we interpret the following n bits as a table index, including some of the bits that are not unused by default. This can only work if the mesh heap is somewhere low in memory, with addresses that fit in fewer bits. Now, to see how our concept works in practice, we have evaluated our working prototype from multiple perspectives. First, we are interested in how our goals are met compared to the other memory safety techniques. We note that none of the others meet all our goals, and most are either imprecise or probabilistic, or use up a lot of memory. Then, we look at the memory overhead. Our solution has a constant overhead, which is very small. All the others that we have looked at use up percentages of the memory, apart from cap. For the runtime evaluation, we have tested our prototype on a synthetic evaluator called Cormark and on the Nginx web engine. The results are comparable to those of the heap-only version of Azan. Finally, other metrics that interest us are the number of objects that are allocated throughout the lifetime of a small to medium-sized program. In our test, Nginx has allocated a few thousand objects, of which only a few hundred are alive at the same time. This leads us to conclude that our table can be big enough for real-world scenarios. Then, from a security perspective, we note that Mesh has perfect precision in its safety checks. Mesh can deterministically detect illegal accesses to our heap from both within itself and from other memory regions, unless of course the optional wraparound and reuse algorithm is used, which makes our temporal safety probabilistic. To conclude this presentation, Mesh is a precise memory safety technique for the heap memory region, which imposes virtually no memory overhead. Its simple metadata lookup algorithm allows its runtime overhead to be comparable to those of mainstream memory safety techniques. Thank you for listening. If interested, you can find more details in the paper.